Hey, flipped chemistry, how you doing? Ready for another lecture? I am. Let's get into it. We're talking today about the mole. And it's not that little furry creature. No. We're not talking about that mole. We're talking about chemistry's mole. And so we're talking about, no, not that one either. Oh my gosh, Mr. L, you're insane. No, we're talking about the mole, which is a method of measuring how much of something you have. And it was come up with by this kind of curious looking dude. Forehead's way too big. I can relate, I guess. But anyway, we're looking at the way to measure how many very, very, very small things you have. And that term is called a mole. I don't know exactly why it's called a mole, but it is. Anyway, you can weigh large objects with scales and you can measure them with flasks, but sometimes you need to know not how much mass there is, but how many actual particles that there are. So we're looking at a way of determining how many actual particles of some substance you have. And so this guy, Avogadro, and his name is just begging to be made into a song, and it has been, it's in the packet. Avogadro came up with a method of finding out how much of something there is. And what he did was he determined experimentally how many atoms of carbon make up exactly 12.01 grams of carbon. And so how many molecules of something there is to make that many grams of its molar mass. And so he determined that the number, actually he didn't finish the work, it was done afterwards and then named after him, or he got the credit because he did most of the work, but the number was 6.022 times 10 to the 23rd, and that number is going to become very, very familiar with you as we go forward in chemistry. 6.022 times 10 to the 23rd of anything is a mole of something. So that's that beautiful number across the bottom of your screen. It's a very, very large number. So a mole of something is not a small amount of something. It's a very, very, very large amount of something, but it's how many atoms of a substance you need for that number of atoms of that substance to weigh its mass in grams. That is the same number as its atomic mass unit, right? So that's how that works, and it will become very useful in the future. So just some additional information. 1 mole of seconds is, what is that? 100,000 million, billion, trillion, 19 quadrillion years. What? That's a stupid amount of time. 1 mole of dimes stacked up on top of each other would reach from the Earth to the Moon 2 trillion times. We just can't quite fathom how big this number is. 1 mole of atoms of carbon, though, weighs 12.01 grams. So it's the number of atoms it takes to have its AMU mass be its mass in grams. Okay, so Avogadro's number, as I've already said, was determined by calculating the number of atoms of carbon it took to have 12 grams of carbon. And so its mass was 12 AMU, and that's because that is 6 protons, 6 neutrons, so 12 grams. And how many carbon atoms weigh 12 grams? Avogadro's number of carbon atoms, right? A mole is the amount of something you need to have it so that its AMU equals the mass of the sample in grams. I've said that like 4 times now. That's the main idea of what we're getting at. Molar mass is the amount of mass 1 mole of a substance has, which is just the sum of all the AMUs of all of the chemicals in that molecule. So, for example, water. Water is H2O. So hydrogen has, we're rounding here, round numbers. Hydrogen has an AMU of 1. It weighs 1 atomic mass unit, and oxygen weighs 16. So what's the molar mass of water? Well, it's twice 1 plus 16, or 18. A mole of water molecules weighs 18 grams. Now there's decimals in there. We're just teaching you the basic idea, right? So a molar mass is the mass of 1 mole of that molecule. Okay, moving on. So what is the mass of 1 mole of quartz crystal? And there's a beautiful picture of quartz crystal there. What is the mole of 1 mass of quartz crystal? Well, quartz is silicon dioxide. So we have to get the mass of silicon and the mass of oxygen. And here I'm going to go out to 4 significant digits, right? So I have silicon is 28.09 and oxygen is 16, but there's 2 oxygens, right? So I've got to multiply that by 2 and then add it all up. And I determined that 1 mole of quartz crystal has a mass of 60.09 grams. So 60.09 is the molar mass of silicon dioxide or quartz. How many moles of quartz are represented by 124.6 grams of a pure sample? Well, if I know the molar mass of quartz, then I can use that. That's how much 1 mole weighs. If I've been given 124.6 grams of it, I could divide how many grams I have by how many grams 1 mole weighs, and I could determine how many actual quartz crystal molecules or formula units are represented in the sample that I've been given. So I just divide. 1 mole is 60.09 grams. I can use bridge notation, which is going to become your friend here very, very quickly. And I can show that 124.6 grams times 1 mole is 60.09 grams. The grams will cancel. And then I can multiply across, and I have 124.6 over 60. And then I just do the division here. And I'll get 2.073556 moles. That's how many groups of Avogadro's number, how many moles of silicon dioxide formula units are in this crystal that I've been given. Well, that's too many significant digits. I only had 4 significant digits and 4 significant digits, so I've got to correct, right? 2.074 moles. So that's how this kind of math works. You're going to do this so many times. You'll be doing math mole conversions a lot this week and next week, and honestly, the rest of chemistry, okay? So here we go. Percent comp is another kind of question you're going to get. What is the percent composition? What percent composition is X of Y? So what percent of water is hydrogen? Well, water is H2O, and we've already determined that the molar mass of water is 18 grams. And so hydrogen is 2 grams of that. And so what percentage is 2 of 18? You just do the division and you get 11%. Okay? So this is another example of a kind of molar math sort of question you're going to be asked, is what percentage is X of Y? And you just look at the molar mass of the thing you're looking for and the molar mass of the molecule, and you find out the percent. Not rocket science. Okay? You can also use percent composition to determine formulas. Now this is a little bit harder, and this will probably take you a couple of whacks at before you understand, but that's okay. So the example here, if a substance is determined to be 20% hydrogen and 80% carbon, using their molar masses will let you determine the formula is CH4, and I'll show you here how to do it this direction. So carbon is 16, hydrogen is 1. If we know that it's 20% hydrogen and 80% carbon, right, then we could show that 4 times 1 plus 16 is a molar mass of 20, and 4 is 20% of that, and 16 is 80% of that. Or you could have looked at this and said, well, 20% to 80%, that's a 1-to-4 ratio. When if carbon is 14, then I need a quarter of that to be hydrogen. So then the hydrogen, there needs to be 4 of those, right? So you can kind of noodle it out a little bit and figure it out, but there are more ways of doing it here. Let me show you a more exacting method, okay? If we have an analysis of an unknown substance, and it has a composition of 15.87% carbon, 2.22% hydrogen, 18.5% neon, nitrogen, why can't I talk, and 63.41% oxygen, then I can determine its empirical formula based on this information. So first thing I'm going to do is I'm going to pretend I have a 100-gram sample of this substance. So that just makes the math easier. I have 100 grams of this mystery substance, and 15.87% of it is carbon. That means I have 15.87 grams of carbon. Okay, so I just turn all these percentages into grams. I pretend I have a 100-gram sample. All the percentages get multiplied by 100%, by 100 grams, and I wind up with the number of grams that I had percentages, okay? So all of these percentages are now masses. Now I can determine how many moles all of these masses represent, right? Carbon has 12 AMU, so 15.87 grams divided by 12 gives me 1.3225 moles of carbon in my imaginary 100-gram sample. So I do that for the others, and I find out that I have 2.22 moles of hydrogen, I have 1.3205 moles of nitrogen, and I have 3.963125 moles of oxygen. Now, this was a pretend sample, but I've been able to determine how many moles of each of those elements would have been represented in my pretend sample. Now, the ratio of moles of these substances is going to be proportional to their relative abundance in the empirical formula. So what I've got to do is reduce all of these decimals down to whole numbers, and that way those whole numbers can become the subscripts in my empirical formula. So let me show you what I mean. I need to find the smallest of my numbers, which in this case is 1.3205. And I'm going to divide all of these other numbers by that smallest number to get all of these decimals down to a ratio of small whole numbers. Okay, so this divided by itself is 1. This number divided by my smallest number is essentially 1 as well. I'm going to round that to 1, right? This 1.68, that's not really pretty. This one, that's 1, and this is about 3. So I've got a relationship here of 1 to 1 to 3 to about 1.5-ish. Well, 1.5 is not a whole number. I need these to be whole numbers so I can turn them into an empirical formula. So what I'm going to do is I'm going to multiply all of these by 2. Okay, I'm going to multiply all of these numbers by 2. And the ones that are already small whole numbers will still be small whole numbers. But this guy will now become essentially a small whole number. So I'm going to multiply them all by 2. And I'm going to wind up with C2, carbon, 1 times 2. Okay, hydrogen, 18.5% became this many moles. This many moles, and then that ratio, and then I'm going to multiply that by 2, which is essentially 3. H3. 1 times 2 is 2, N2, and 3 times 2 is 6. C2H3N2O6 is my best guess as to the empirical formula that would represent these percentage compositions. Okay, if you need to see that again, stop, go back, play it again, or talk to me, ask some questions in the comments field. I'll get back to you as quickly as I can. Alrighty? And now you're ready to do Lewis structures and see if you can figure out how those elements would fit together and make a model or a diagram of the shape. Okay, that's it. Let me know if you have any questions. I will see you tomorrow. God bless you. Jesus loves you, and so do I.